Hi everybody, today we're going to be going through these chemical kinetics test practice questions, hoping this will be helpful to some of you out there. Alright, so this first set is just an idea of comparing how much of something is being made and how much if something is being produced. So I'm not going to do all of these answers, but I'll do the major ones. Here we have initially 0.124 moles of N2O5. So we need to get twice as many moles that are consumed are going to be produced. So find the difference here. 0.124. I need a calculator. Should have had that ready beforehand, I guess. Okay. So 0.0124 subtract 0.00092. And then we get a value of 0.032, but it's a 2-to-1 ratio, so we're going to multiply that final number. You got to watch out for your brackets here. Multiply that number by 2 because you get 2-to-1 ratio. So that's going to be 0.0064. And then we're actually going to divide it by 2 if we want to do the oxygen. So 0.0016. And there we go. So that is how much O2 has been made because that's how much N2O5 has been consumed. If we do this for the last option, because we are going to need that last number later, we're going to take the total difference, 0.0124, subtract the final remaining amount, 6. We've got a change of 0.0118 in total, and so then if that change is converted into product, there are 2 NO2s for every N2O5 that's consumed. And there is a half of an oxygen, so 0.0059. Okay, so then use the data and the balance equation, calculate the concentration. Okay, you can go through and calculate all of those. That's the major idea. The numbers should continuously go up on the left in the 2 right columns. What is the average rate of decomposition over the entire 100-minute intervals? So let's just do the entire 100 minutes. So formation of nitrogen dioxide, we can take our final value, 0.0236. That's how many moles per liter we created, divided by the total time of 100 minutes. And we just get 0.000236 moles per second, per liter seconds. So that's all you need to do for that one. So what is the average rate? That's our NO2. You can do the same thing for the oxygen, just divide the two numbers. What is the average rate of decomposition and formation in the first 20 minutes and the last 20 minutes? So that's where we might find something interesting in terms of the comparison. I'm going to do, again, 0.0124. Oh, I should put that bracket in, as I know I'm going to need it. And take away the 20-minute timer, and then multiply by 2 for this one, 0.0112. And I guess I can do the divide by 2, why not? Divide by 2. And we're going to get 0.0028. So that's our 2 values. So what's the formation in the first 20 minutes? Decomposition and formation. So you could also figure it out in that way. You could also figure it out from taking the change here. So the change of, which I almost have written out. So this change is a change of 0.0056. So we could also take that 0.056. So 0.0056 moles per liter divided by 20 minutes. Divided by 20 minutes. 0.28. And this is my N2O5. And we also know that the N2O5, we know that if we take the 0.00028, multiply that by the mole ratio, we can also find the rates that way. Oh, not O. Sorry, NO2 is the one that has 2. So then that's 0.00056. And we could even do the same thing for oxygen, but oxygen is half of it. So that's our NO2. And this one is 0.00014. That's our O2 rate. Okay. If the decomposition of NO25 gas occurs at 0.350, what is the rate of formation of NO2 and O2? So that's the same thing we just did. You would just be converting by the ratio. So we would just take the 0.350 and then multiplying by the 2 NO2s per 1 N2O5, or whatever that gets you. Do the same thing for oxygen. Hopefully that's good enough. All right, let's keep moving along. We don't want to be here all day. If ammonia gas reacts with this rate for the ammonia with oxygen, what is the rate of oxygen gas under this oxygen gas reaction in these conditions? This is again a ratio question. So we're just going to take that, multiply by the ratio of what we are interested in, oxygen, over what we have, the ammonia. And so we end up with 0.19 times 5 divided by 4. They have almost the same rates because they have almost the same ratio. Right, it's 5 and 4. It's almost a 1-to-1 ratio. Okay. What is the rate of formation of water? We could do that as well. What's the rate of production of nitrogen monoxide? Okay, that's fine. Nitrogen monoxide, we should have a 1-to-1 ratio with the ammonia, so this will be 0.190. Nothing exciting there. What is the activation energy of the forward reaction for A, B, C? So here's our A and B, A plus B, and this is our C. So we can see that C has higher energy than the A. It looks like to me that this is supposed to be sort of like 25-ish. And I was hoping for a straight line there. Oops. 25, and then this is our activation energy. So this is our activation energy. So let's call this 25, and let's call this 250. So then the activation energy is 250 minus 25. That gives us 225 kilojoules, sometimes given in kilojoules per mole. Depends on how the stoichiometry works out. What is the heat of the reaction? So that heat of reaction is going to be between the product and the reactant. So the product here is at 100. This one's at 25. So we're going to say that that's 100 minus 25, giving us positive 75. Remember that this is going to be important as to whether it's positive or negative. Is the endothermic or exothermic? And it is endothermic. The product has a more potential energy stored in it based on the arrangement of atoms. Explain why gasoline can mix with air and not ignite while sitting in a car, tank in your car, but explodes in the piston of the engine or ignites when it is touched by a flame. So this is a lack of activation energy. Energy. Also phase matters. Phase matters. In the piston, gas is in aerosol spray. So an aerosol spray is technically a liquid, but the particles are so separated that they're a gas, and I believe even some of it's gaseous as well. So let's put gas. And that means that the atoms have a much higher surface area. The molecules have the highest surface area they can because each molecule is completely separated from the other. Okay, draw and label a potential energy potential diagram, reaction coordinate diagram showing the enthalpy of change and the activation energy for this reaction. So the reaction looks like this. And just go reaction, and then this is our potential energy. We have a enthalpy of reactants is only 20 kilojoules. Oops. So let's put that down here, 20. And then the products are 45. So we're expecting something that looks like that. Now, can we even figure out the activation energy? No, you can't. That's impossible. Impossible. This we can do. And that would just be the 45 minus 20 to give us positive 25. Okay, let's look at the factors of change. So how does the theory, so thinking about these atoms must collide, atoms must have sufficient energy, collisions must have correct geometry. How do the different factors apply? Chemical nature, this really is going to be a change. Let's see if I can type this one. Chemical nature changes the energy requirements. So that's why that's part 2. So 2 changes the energy requirements. Temperature, more particles have sufficient energy. Sufficient. Okay, gas pressure. This is sort of 1 and 2. More particles equals more particles, more collisions, more with energy. Okay. So the more particles you have, the more particles you have at the correct energy level. So that's what I'm trying to get at there. Okay, surface area, this increases, so this is 1 and 3. More possible collisions, with higher area. And then a catalyst is energy, so that's 2, reduces energy required. So more reactions happen. And then mechanical action is probably more like mostly 3. Increases the disorder, which improves likelihood of correct geometry. Something along those lines. If you want any more details on that one, go ahead and ask. Okay, not that you can ask from home right now because this is a video, but you know what I mean. Let's see if I can get this to look a little nicer. Not quite, eh? Okay. And they do not have formatting, which would be nice, but okay. Oops, that was... All right, it'll have to do. Something like that. Okay. Following mechanisms proposed, what would happen to the rate as the concentration of Q is increased? No effect here. So we mostly have no effect. Let's see if I can put a number. Okay. So no effect. B, write the net reaction. This would be P plus 3Q. X cancels out, and A cancels out. So then X cancels Y plus Z. That would be our final net reaction. Was a rate determining step. A plus 2Q is our rate determining step. Slowest step. Y is step 2 slower. So this might be, there's a lot of different reasons, but one thing that you can look at right away is you realize that this is a 3-component reaction. 3 molecules reacting. less likely than the other two-step reactions. And then what are the reaction intermediates? Intermediates, so we have A, and X. They are produced and consumed. Okay, so in this mechanism, identify the catalyst, and we see that platinum is provided and then removed. What's the reaction intermediates? So any of these platinum compounds are intermediates. Platinum, C2H4, those would both be intermediates. And then the final reaction is C2H2 plus 2H2 gives C2H6. Pretty good, pretty important chemical reaction actually. It's one of the ways you can open up a double bond. Okay, we're given some data here. We have two that are the same, and so we can use that to find A. So in this one, we only look at this one, that's times 3. We look at this one, just use your calculator to figure out what's going on there, divide by 0.041, and we get, oops, not that, 0.12. Oh, I use times, of course. I'm like, what is going on? All right, there we go. All right, so that's about 3, right? About 3 times. And sometimes with experimental data, you'll notice that they are not perfect numbers. So to me, that means that A is to the exponent of 1. If you want to use the Desmos solver, that's great. But in this case, I don't see much reason that we have to use the Desmos solver. So that would be my suggestion here, that we would just put a little A and say that's a 1. And then we still don't know what B is because we didn't make any changes here. So let's grab another one and do another experiment. Let's grab in blue this pair and this pair. So it's going to be trickier. We have an increase in rate. So I'm going to do this thing this time. Rate equals K times A to the power of 1 times B to the power of B. And then I'm going to punch in my numbers. So we have a doubling of A, we have a doubling of B, and the rate, 0.33 divided by 0.041, is 8 times. So that's 8. So 8 on the rate. So that means that the 8 has to be equal to 2 to the power of 1 and times 2 to the power of B. Okay, we can do some little division here. Get rid of that one. We got 4 equals 2 to the power of B. So B must be 2. And then we're done. Okay, so that's great. So that's that one works out. So now we can say that says what's the rate law? So we're just going to say rate equals K times A times B squared. Excuse me. So we have one more to do. We have a big one here. We're going to look for our commonalities. Here's a common one. Here's a common one. And this one's different. What do we got? We got 2 times. And we have 0 change, right? 1. So what does that mean? That means that we are starting off with a flat 0 on the BR. Okay. So if you need me to go through that, then come talk to me later. Let's look at the next one. We have this one and this one are the same. This one and this one are the same. And this one has a change. This one is times 2. And so let's look here. That looks like essentially times 2 as well. So E negative 4 divided by 5.7 E negative 5. Yeah, so that's about 2. So that's a power of 1. To make sure that they're equal, they have to be they have the same exponent. And then finally, we need one that does something different to the A. So I'm looking. Okay, look at this one. So if we take this and this, they're the same. this and this is the same, and this is times 2. And so then we look here, and we have 2.3 to the power of negative 4 divided by 5.7 times negative 5, and that gives us a multiplier of 4. So that looks like 2 to the power of 2. So I'm going to say that the rate, the order with respect to this is 2, respect to BR is 0, respect to H is 1. So the rate law is rate equals K times CH3CO CH3 to the power of 2 times BR2 to the power of 0, sometimes not included because it's power of 0, H plus to the power of 1. Find a rate law, or a specific rate constant. So we just need to punch in some numbers, 0.3 times 2 to the power of 2, 0.050 to the power of 0, 0.050 to the power of 1 equals, and there's K equals 5.7 times 10 to the negative 5 for the rate. 5.7 e negative 5 divided by 0.3 squared times 0.05 to the power of 0, nothing to see there, 0.050 to the power of 1. Okay, so that means that K is equal to 0.013. So what's the rate in 7? All we have to do is take all of our values together. 0.013 times 0.5 squared. We can ignore the b. If you want to include it, you can, but the 0 will make it worth nothing. And 0.020 to the power of 1. Okay, 0.013 times 0.5 squared times 0.1 to the power of 0 if you like, it doesn't matter. 0.02 to the power of 1 equals 6.5 times 10 to the negative 5. Okay, so that would be our rate. What is the concentration of CH3COCH3? Just do that one in purple real quick. So we have a rate, 6.2 times 10 to the negative 5. We have a K, 0.013. We do not have this, CH3COCH3 to the power of 2. And we do have the other values. The only one that matters is the H plus. So then we do a rearrangement, 6.2 negative 5 divided by 0.25 divided by 0.013. That gives us this number, 0.019. And we're going to take the square root of that to find CH3. CH3. So watch out for that square root step. That's definitely one that a student will make a mistake on. And I can't do a square root very easily on this calculator, so I do use the power of 0.5. So my value is 0.14 equals the concentration of CH3COCH3. Okay, hopefully that helped you out, and we'll talk to you in the next one.